Let's look at the following member of the family of logistic maps, namely the function f of x is 4 times x1 minus x. So this coefficient 4 was all the way to the right of our bifurcation diagram from the previous video. So this is the most chaotic, the most exotic member of this family of logistic maps. So what we're going to do now is we're going to look at the orbits of two neighboring points. So I have this little diagram over here where I calculate the orbits of this point 0.3 and then the next point in the second column 0.301. And then you see initially the orbits are relatively close together. So as you would expect, if you start close together, you will also in the beginning end up close together. But here something interesting is happening. You see that as you move further and further down this column here, if you do more and more applications of your map, eventually the values will end up being completely different and completely uncorrelated. So yeah, that's a very interesting behavior for this particular logistic map. Now you might say, okay, well, if you want to fix that, let's just simply take 2 points which are even closer together. So let's add a couple of zeros here before the 1, and then make another table like this. And then you see that, okay, the orbits will stay closer together for a longer period of time, but eventually the same phenomenon creeps in. Eventually you will still end up with two different orbits which are completely uncorrelated and which explore completely different regions of phase space. So that's very interesting, or very problematic also, if you want to say, because what this means in practice is that even though you have an equation which is fully deterministic and well known, like this equation here, you would think, okay, given the fact that I know this equation, I will be able to calculate exactly what happens for a certain initial value x0. So what this little numerical experiment has shown us is that this is not really true in practice, because there's two problems. First of all, your initial condition x0, well, you might have some issues with measurement errors if you want to model, for example, a physical system. So there might be a small error in your initial condition. And then you see that this map here basically amplifies that error until you basically cannot predict anymore what will happen in the long term because the map is so chaotic. Or another issue is simply the fact that if you calculate this on a computer, you have finite precision, and this finite precision will also be equivalent to some sort of small errors. And the issue with this map, again, is that all of these small errors, they will eventually get amplified by the map such that it's basically impossible to make any long-term prediction about the behavior of a certain orbit. So that is in essence what we mean by chaotic behavior, the fact that you have a very sensitive dependence on initial conditions, meaning that even if you have a fully deterministic system, in practice that turns out to be not useful because you cannot calculate the very long-term behavior of a certain system, because all of your errors, measurement errors, numerical errors, they all get amplified such that it becomes basically useless to make predictions. Okay, so that's a very important phenomenon. Of course, not all systems have this chaotic behavior, so therefore it would be interesting to find some way to quantify to what extent a system is chaotic. And that's what we're going to do in the rest of the video. We're going to try and identify a metric for how chaotic a certain system is. So it will probably come as no surprise that the derivatives play an important role there, because they also play the role in the stability of fixed points. So we suspect that they also play a role if you have chaotic systems, as we will see now. So what I would like you to do is pause the video and write down sort of an approximation for our map f of x in the neighborhood of the first point of our orbit, the initial condition x0. And then once you have such a Taylor expansion, plug in two neighboring points, let's call them xa and xb. And then using this Taylor expansion, investigate what will happen to the distance between these points before you apply the map and after you apply the map. So we can write down the following approximation, that our f of x minus f of x0, the point around which we approximate our function, is roughly equal to the derivative at that point x0 times x minus x 0. So this is our first order Taylor expansion of our map. So now we plug in two neighboring points. The first point is xa, so we have f of xa minus f of x0 roughly equal to f of x0 xa minus x0. And then we do the same thing for the neighboring point b, f of xb. And now I'm getting slightly bored. Okay, copy, paste f of x0 xb minus x0. So now what we would like to do is make a statement about distances between these 2 points xa and xb before and after the map. So what we're going to do is we're going to take these two equations and subtract them from each other. And then we have that f of xa minus f of xb is more or less equal to f prime at the point x0 xa minus xb. Okay, very basic trivial calculations, but the important thing here is the interpretation, because what we have here, this term over here, is the distance between the two neighboring points a and b before you apply the map, and over there you have the distance after you apply the map. So this simple equation tells us that they basically related with this multiplicative factor here, which is the value of the derivative at the point x0 around which you develop the series expansion. So this is very interesting because, of course, this will tell us what will happen to neighboring orbits. If this is a very big number here, then it will tell you that after you apply the map, small distance between these 2 points will get amplified such that this distance here becomes much larger. Of course, this was also at the crux of the argument that we used when we looked at stability, because for stability we said, okay, then x0 is a fixed point, and then if this magnitude is smaller than 1, then the distance between neighboring points will get smaller and smaller. A very similar argument we had there, but here it's in a slightly different context. x0 is not a fixed point, it's the first point of our orbit. So obviously the orbit continues. If we have x0 and then we apply the map, we end up at the point x1. It could be that that point x1 is pretty far from the point x0, so our series expansion is no longer valid. But of course what we can do is we can make a new series expansion around the point x1 and then play the same game, because around the point x1, what will now determine the amplification of the distance between neighboring points is f prime at x1. So if you want to quantify how chaotic a certain system is, or more specifically how chaotic a certain orbit in a system is, what we're going to do is we're going to calculate some sort of average value of the derivative for the different points in the orbit. So you have x0, x1, x2, and so on and so forth. And you want to calculate some sort of average value of the derivative at each of these points. Now, typically, this averaging is done in a geometrical sense, and the geometrical average of all of these points is called the Lyapunov number. So this is denoted by, for example, L of x0, x0 being the initial condition of our orbit, and it's calculated by doing some sort of geometrical average, as I told you, for the different derivatives, or their magnitude rather. So we're going to calculate, for example, f prime around the starting point of our orbit, multiply that by f prime at the next point. And let's first look at k different points in our orbit. So the first k points, so this is then the point k minus 1. So we multiply all of these k values together. And then we take the geometrical average, so we raise that to the power 1 over k, right? This will give us a certain number, and we can keep on repeating that procedure for k values that are larger and larger and larger. So what we can look at is the limit of the number of points that we're looking at in our orbit going towards infinity. If this quantity has a well-defined limit, then this limit is called the Lyapunov number. And again, it's some sort of average value telling you how much distances between points get amplified if you apply the map. So that's the Lyapunov number. Sometimes people also like to work with the Lyapunov exponent. Yeah, and that's just a simple transformation. That's basically the natural logarithm of this Lyapunov number. So this will be a limit basically of 1 divided by k times sums of logarithms of the values of the derivatives at all of the different points. So can we now define a criterion based on either the Lyapunov number or the Lyapunov exponent that tells us when do we have a system which is chaotic? The answer is, of course, yes. Simply pause the video and see if you can formulate the answer. So if we have a Lyapunov number which is bigger than 1, and after the logarithm that corresponds to a positive Lyapunov exponent, then we have chaotic behavior, because then the factor that relates the distances, here we have it, the factor that relates the distances on average between before the application of the map and after the application of the map is bigger than 1. So therefore this distance gets amplified. And that's the hallmark of chaos, the hallmark of having sensitive dependence on initial conditions.